Welcome to the deep dive. Today we are jumping right into the epicenter of the global energy transition. We're talking about the race for critical minerals. I mean, if you've looked at any headlines recently, you know this scramble is just intensifying. You have countries, you have companies, all fighting to secure stable supplies of lithium, copper, cobalt.
And all those vital components like the platinum group elements, the PGEs, and of course rare earth elements or REs.
Exactly. We need all this stuff for batteries, for next-gen magnets, really for the entire green infrastructure of the future. It's almost like a resource war, but fought with spreadsheets and drill cores.
Right. And while I think most people assume the biggest challenge is just, finding a new deposit and digging it up, our stack of research today argues that the real bottleneck is actually far more subtle.
And more critical.
Way more critical. The constraint isn't always extraction. It's understanding the fundamental geological architecture that dictates whether a resource is actually, economically viable in the first place.
And that is the core tension we're diving into. The really surprising part is that the traditional tools the industry has relied on for years they're proving to be too coarse, too zoomed out. So our mission today is to unpack why one specific high-resolution technique, it's called micro-XRF, is certainly shifting from being this niche lab tool to a completely non-negotiable strategic asset in this global race.
We're really going to be exploring what geologists call the resolution gap. And think about it this way. The difference between a project that gets funded and a resource that is permanently stranded, unprofitable.
Yeah.
That difference often comes down to mineral features that are just a few microns across. We're talking tiny grains, microtextures, specific chemical signatures. If you can't see those few critical microns, you're basically making multi-billion-dollar capital decisions with incomplete information.
So let's start there. Let's talk about the standard workhorse, the tool the mining industry has relied on for, the last 2 decades for this kind of quick assessment, the XRF core scanner.
Yeah, these scanners are, they're incredibly useful for initial exploration. They're fast. They give you quick elemental profiling across drill cores at the meter scale.
So a broad overview.
A very broad overview. They let organizations assess huge volumes of rock really quickly, which speeds up the preliminary stages of defining a new exploration target. They were designed for bulk materials.
But that's the key, right? The shift to critical minerals where the value isn't measured in tons of ore, but in trace elements. That's exposing the limitations of these legacy tools.
Yeah.
So can you explain functionally, why are these core scanners just too coarse for today's challenges?
It really all comes down to physics and design limitations. A traditional core scanner uses what's called a slit-based line scanning approach.
Okay.
So when it analyzes a section of rock, the system is forced to average the elemental signal across a pretty large area. The resolution footprint can be anywhere from 200 all the way up to 1,000 micrometers.
1,000 micrometers. So that's a whole millimeter. That might sound tiny to us, but in mineral chemistry, that's vast, isn't it?
It's an enormous slice of rock. It's millimeter scale averaging.
So why is averaging across a full millimeter such a fundamental problem when we're chasing these elements?
Because the features that actually determine the economic viability, they're exponentially smaller. We are talking about precious mineral grains, the RDE-bearing minerals, the tiny micro-inclusions of PGEs or those lithium-rich silicates that only measure between 2 and maybe 10 microns.
They're microscopic.
Exactly. And these micro features, they aren't just trace elements, they are the controls. They determine your actual grade, they influence how you have to process the ore, the metallurgy, and they ultimately dictate your financial return.
So if a core scanner averages a crucial 5-micron particle that contains all your value with, say, 995 microns of worthless rock,
then the signal you get is fundamentally diluted. It's distorted. You lose all the critical context.
and the consequences of relying on that blurry resolution, I imagine they're financially catastrophic down the line.
Oh, absolutely. We see it all the time. Companies encounter these massive surprises later in the development cycle. They built a resource model based on averages, and then they find out the specific mineral phase they need to extract is way more complex than they thought.
So they might have underestimated the concentration or...
Or misunderstood the mineralogy. Or, even worse, built a multi-million-dollar processing mill, a concentrator, a flotation circuit that is totally unsuited to the actual physical form of the mineral.
That's where the analogy really works then. If you're looking for a high-value coin in a warehouse, the old XRF core scanner is like a satellite photo. You can see the warehouse, sure, but you can't resolve the coin. The crucial details, which are literally hiding in plain sight, are invisible because your analytical camera is just too zoomed out.
And the cost of missing that coin or that 5-micron grain of monazite can lead to $500 million of wasted capital expenditure. It's a huge problem.
Okay, so if the problem is resolution, the solution has to be high-resolution analysis that's engineered for that microscale. And this brings us to the new analytical paradigm, embodied by tools like the Atlas Apex X, a high-resolution micro-XRF system.
Right. It shifts the whole workflow from just bulk elemental analysis towards precise mineralogical imaging.
This feels like a fundamental leap.
It is. We are transitioning from simple line scanning to focused spot-based analysis. The technical distinction is profound. We're moving away from those broad slit-based footprints that cause all that coarse averaging.
And moving toward what? A tightly focused beam.
A very tightly focused beam. And that's how we get the ability to truly resolve these fine-scale mineral textures.
So instead of a wide line, you're using almost like a high-powered microscope beam. What are the specific engineering steps that make this kind of microscale imaging practical for, high-volume geological samples?
Well, there are three main functional steps. First, the beam size itself has to be ultra small. We're talking less than 10 micrometers to capture those individual grains.
Okay, step one, tiny beam.
Step two, the system needs superior distortion-free excitation geometry. This is essential because it gets rid of the blurring and artifacts that plagued older systems, so you know exactly where the signal is coming from.
And the third step, this has to be crucial for the energy transition minerals specifically, because so many of them are chemically light, right? Like lithium, aluminum, silicon. Standard XRF struggles with those.
That's the low Z sensitivity challenge. You're spot on. A lot of critical mineral hosts fall into this low atomic number category. To reliably analyze them, these advanced systems use vacuum-enhanced detection.
You're removing the air.
Exactly. By removing air, you remove the biggest interference for those light elements. It dramatically boosts your ability to see key mineral systems, like many of the lithium-bearing silicates, with very high confidence.
That sounds incredibly detailed, but, the traditional trade-off for high resolution is always speed. Doesn't this process take weeks? Does that negate the advantage of the old fast-core scanners?
That's where the advanced detector technology comes in. Modern micro-XRF systems use multiple large silicon drift detectors. They're designed specifically for high count rate mapping.
So you get speed and resolution.
You do. The result is you can generate these comprehensive, high-resolution maps over a sizable area of rock in just a matter of hours or days, not weeks. That combination of speed and resolution is the real disruptive element here.
Okay, so high-resolution data, and you get it quickly. But what's the ultimate output? You're not just getting raw element counts anymore, are you?
No, not at all. You're generating hyperspectral 2D chemical imaging. Then that image is processed against massive mineral reference libraries. Some have thousands of different mineral phases. The computer classifies those elements into actual minerals.
So the final product isn't a list of elements.
No, it's an explicit map of the mineralogical architecture.
Yeah.
You can see where the monazite is, where the spodumene is, and critically, how those minerals are associated with others. That map becomes a predictive, strategic asset for the processing plant.
Let's focus on some specific metals then, because I think this is where the economic difference becomes glaringly obvious. Let's start with rare earth elements. We know they're essential for magnets, but where do they actually live in the rock?
REEs are so frustratingly elusive. They're almost always contained in what are called accessory minerals, things like monazite, xenotime, bastnasite.
These classic micron scale grains you mentioned.
Yeah, those are the ones. A traditional core scanner just blurs that REE signal across a millimeter, giving you a general sense that, yeah, REEs are present. But the MicroXRF, it isolates and maps the precise location, the density, and the association of those individual grains.
And that's vital for processing later on.
It's everything for optimizing froth flotation or magnetic separation methods down the line.
Okay, application 2. Niobium and tantalum. Crucial for high-performance alloys, electronics. These are often in oxides like columbite or tantalite.
What's truly fascinating here is that the chemistry can vary significantly even within a single crystal. Yeah. One edge of a crystal might be rich in niobium, while the core is tantalum dominant. These subtle micron-scale chemical zoning variations fundamentally impact how that mineral responds to processing. MicroXRF can map these internal variations.
Which lets the metallurgist predict behavior.
And design circuits that maximize recovery and, just as important, minimize waste.
Okay, now let's talk lithium. This is maybe the most critical piece for you, our listener, to understand, because it presents this major technical headache. If XRF struggles with low atomic number elements, and lithium is the lightest solid element, how do these systems help? Doesn't the system just fail here?
That's a perfect observation. And you're right, lithium itself cannot be detected by XRF. This is where the strategy has to shift from direct elemental analysis to, well, clever mineral identification.
Yeah.
If you're relying on coarse XRF data for lithium, you are absolutely flying blind.
So what's the strategic workaround? How do you turn a blind spot into a high-resolution map?
You use proxy mapping. The critical lithium mineral hosts, spodumene, petalite, lepidolite, they all have highly specific, detectable proxy signatures.
So you're looking for their friends, not them directly.
Exactly. They contain unique combinations of aluminum, silicon, potassium, sometimes fluorine. The micro-XRF, with its vacuum-enhanced sensitivity, maps these proxies with such high resolution that it can differentiate the valuable lye-bearing silicates from the worthless silicates right next to them that look almost identical.
And it must be about more than just identifying the mineral, right? It has to be about its condition.
Precisely. It reveals the microtextures and, crucially, those reaction rims around the grains. These little alteration zones are often indicators of potential processing inhibitors. They can slow down extraction or lead to poor recovery forecasts.
So you're not just finding the lithium, you're
No.
predicting how easy and how cost-effective it will be to get it out.
Now you've got it. It's a predictive tool.
Okay, let's look at platinum group metals, PGEs.
Yeah.
These are often described as the invisible elements because they occur as these tiny sub-10 micrometer specks.
Yeah, think about it. A tiny grain of palladium or platinum trapped inside a massive sulfide or chromite crystal. These sub-10 money inclusions are completely invisible to coarse scanners. Their signal is just averaged out into nothing.
But MicroXRF can see them.
It resolves them directly, and this changes exploration completely. Instead of relying on a bulk chemical assay that just says, PGEs are here, you can actually map their deportment. You can see how they occur.
Which lets companies evaluate the potential much, much earlier in the process.
Profoundly earlier.
All right.
It completely changes investment planning.
And finally, let's touch on the importance of mapping those alteration zones and elemental gradients, the history book of the rock itself.
Right. These reaction fronts are the key to understanding metal mobility and extraction. Ores are not static. They're the product of complex chemical processes that create these zoned alteration envelopes.
And MicroXRF gives you a micrometer scale view of that history.
It does. I mean, look at the example from the high-grade gold site at the Brucejack mine. The mapping there revealed micrometer scale distributions of gold, silver, lead, and zinc. That level of detail showed that the gold was often closely associated with sulfide-hosted base metals.
Seeing that specific relationship at a 5-micron resolution, that must allow geologists and metallurgists to optimize processing in a way they just couldn't before.
It's something that bulk assays simply cannot achieve. It's a different world of information.
Okay, so we've established the technical and the functional superiority of MicroXRF. Let's pivot now to the strategic and competitive impact. Why is this capability no longer a lab luxury, but a business necessity in the critical minerals sector?
It fundamentally boils down to reducing risk and uncertainty in massively capital-intensive projects. I mean, for critical mineral projects, which often cost hundreds of millions, even billions of dollars, the ability to eliminate ambiguity about your resource model is priceless. So when organizations adopt this kind of micro-scale clarity, they see 4 huge organizational gains. First, they get genuinely accurate resource assessments.
Right.
Second, they see a massive reduction in the uncertainty that plagues feasibility studies, which are the blueprints for major investment. Third, this leads to dramatically higher confidence in crucial CapEx decisions.
So less chance of poor capital planning.
Much less. And finally, achieving all the certainty up front accelerates the timeline from exploration all the way to final production.
And that speed is paramount. We're not just talking about chemistry anymore. We're talking geopolitics. In a marketplace where strategic minerals are rapidly becoming, national security assets, getting to market faster with higher confidence is everything.
Absolutely. The research makes it crystal clear. The strategic advantage is speed and certainty in a geo-competitive race. If you can move from a promising drill target to a fully financed operational mine faster than your competitor, you secure the market share.
And potentially national supply.
Potentially. If you rely on coarse analysis, you spend years refining your mineral model, costing you time and money. MicroXRF systems accelerate that entire resource evaluation, allowing organizations to de-risk projects more effectively and, crucially, secure project finance much faster.
So the ultimate message here is that organizations involved in the energy transition simply can't afford to compete on outdated information. To win this strategic race, the analysis has to happen at the exact scale that dictates the mineral's economic behavior.
That is the core takeaway. The industry is moving past the point where millimeter scale averaging is good enough. High-resolution micro-XRF systems transform geological information from a descriptive, static report into a predictive, dynamic, strategic asset. This is how you convert a geological curiosity into a reliable, bankable resource.
What a fantastic journey through this transformation of geological analysis. The shift from imprecise millimeter scale averaging to crystal clear micron scale imaging has, it's fundamentally changed how companies approach resource viability and manage risk in this new energy age.
And that leads us to a final sort of provocative thought for you to consider. If the difference between success and failure in critical mineral extraction lies in the visibility of just a few microns, what other crucial, invisible details in your own business, your own strategy, or your research are you currently overlooking? Are you relying on analytical tools that are just too coarse to reveal the fine-scale details that actually drive your success or failure? It's worth thinking about the resolution of the data you use every single day.
A truly great point to end on. Thank you for joining us for the deep dive. We'll catch you next time.